Hello, I'm Wan Zhang from Seoul National University. The title of our paper is TIDY, Publishing a Time Interval Dataset with Differential Privacy. This is a joint work with Suyong and my advisor, Kyusa. This is the outline of my talk. After the introduction, I'm going to provide the drawbacks of existing methods, and I will present the proposed algorithm. Finally, I will report the experimental results. A time interval consists of the start time and the finish time of an event. Log data in many applications contain a series of events with time intervals. For example, video streaming services such as YouTube and Netflix can save the watching history with the time span of watching video. In addition, many other types of services such as Google Maps Timeline save the log with time intervals. Exploiting temporal information plays an important role in many areas such as recommended systems and web search and so on. However, such log data with temporal information usually contain private information. So we propose the TIDY algorithm to publish time interval dataset with satisfying epsilon differential privacy. This is the definition of epsilon differential privacy. For every pair of inputs D and D prime that differs in only one row, and for every output D tilde, a differentially private algorithm should satisfy this condition. The intuition is that adversaries should not be able to use the output D tilde to distinguish between any D and D prime. So these probabilities should be similar to guarantee epsilon differential privacy. Before formally defining the problem we addressed, I'm going to introduce a frequency matrix representation for time interval dataset. A set of time intervals can be represented by a frequency matrix, which has the number of time intervals for every pair of the start and finish time. This value 2 represents that there are two time intervals which start at time 1 and finish at time 4. We next provide the problem statement of publishing time intervals via differential privacy. Given a T by T frequency matrix M generated from a time interval dataset and a privacy budget epsilon, our goal is to publish a noisy frequency matrix M tilde with epsilon differential privacy. So the original frequency matrix cannot be inferred from the published noise frequency matrix. There are 7 types of count queries with standard predicates for temporal databases, such as time slice, start, and so on. A query region is represented by a rectangle on the frequency matrix. To compute the result of a query, we sum up the elements in the query rectangle. We want to reduce the errors of the standard count queries while preserving differential privacy. I'm going to introduce some applicable methods for our problem and discuss their drawbacks. We can ensure the differential privacy by simply applying the Laplace mechanism to the frequency matrix. This is the pseudocode for the naive method. It adds Laplace noise to every entry of the frequency matrix to ensure the differential privacy. However, it results in large noise errors for the count queries that need to sum a large number of entries in the frequency matrix. The noise error for answering a range query is proportional to t squared divided by epsilon squared. It shows that we cannot use this naive approach for large-scale data. To reduce the noise error, existing methods reduce the number of noise injection by partitioning the frequency matrix into rectangular regions and adding noise to each partition rather than to each cell. However, if we reduce the number of entries, we cannot exactly reduce the original data, even if we do not add noise. This error is called the structure error. To answer a query, existing methods estimate the count of every element in a partition by averaging the frequency in the partition like this. Consider this query rectangle. The correct answer of this query is 40. In this case, the estimated result is 64, even before we add the noise to each partition. It means that the structural error exists because of the non-uniformity of the data. So it is essential to reduce the noise error while minimizing the increase of structural error. Now I'm going to present our tidy algorithm. We aim to reduce the aggregated noise error as well as suppress the increase of the structural error. Today, we will introduce the following key ideas of the tidy algorithm: triangular grid partitioning, frequency vector representation, and the refinement algorithm. Each of these techniques is designed to reduce noise error or structural error. First, we discuss triangular partitioning. Tidy partitions the frequency matrix into B-square triangular regions, where B is the branching factor. This is an example of triangular partitioning when the branching factor is 2. The frequency matrix is partitioned into 4 triangular submatrices. Each partition is represented by using frequency vectors, and we will discuss it later. We compute the branching factor to minimize the total estimated error, which is represented as the sum of noise error and the structural error. I'm going to introduce our frequency vector representation. For each triangular partition, our tidy algorithm computes 3 types of frequency vectors named start time, finish time, and duration frequency vectors. These vectors contain the number of time intervals for each start time, finish time, and duration. For example, the first entry of the start time frequency vector represents the number of time intervals start at the first timestamp, which is equal to the sum of values in the first row of the frequency matrix. Likewise, the second entry of the vector represents the sum of elements in the second row. Similarly, we can see that these vectors are the row-wise, column-wise, and diagonal-wise sums of the frequency matrix. By using the frequency vectors, our tidy algorithm significantly reduces the structural error. Again, we consider this query rectangle. First, I'm going to investigate the right lower triangular partition in this frequency matrix. In this query region, the correct answer is 10. Recall that the finish time frequency vector contains the column-wise sums of the frequency matrix. So we can exactly compute the sum of elements in these 3 columns by summing up the first 3 entries of the finish time frequency vector. It means that there is no structural error in this partition. Similarly, the sum of values in these rectangles can be computed by using row-wise and column-wise sums. It means that we can compute the sum by using frequency vectors without the structural error. So the structural error occurs only in a single element if we use the frequency vectors. We also showed that tidy algorithm may cause the structural error in at most a single partition like this. However, the state-of-the-art can cause the structural error in this amount of partitions. So we can reduce the structural error by using the frequency vectors. To reduce the noise error as well as the structural error, we propose an algorithm for frequency vector refinement. Similar to the previous work, we formulated the refinement problem as a maximum likelihood estimation. We minimize the error distance between the estimated vector and the noise vector because it is proportional to the negative log likelihood of the observed noise vector. Because the sum of all elements in the vector is the number of time intervals in the partition, we introduce this equality constraint. In addition, we impose a non-negativity constraint because the original frequency vector is non-negative. Please refer to our paper for detail. There is an iterative algorithm to find the solution of the refinement problem. However, it takes t² multiplied by the number of iteration time to compute the solution. So we propose a simple and efficient method to find the solution in t log t time. The solution is obtained by adding a scalar value to the noise frequency vector and converting all negative values to 0. To do this, we proposed a method to find the scalar value delta k within t log t time. This is the overview of the tidy algorithm. In this presentation, we have addressed some important modules of the tidy algorithm. We also proposed the reconstruction algorithm to reconstruct a frequency matrix from differentially private frequency vectors. Moreover, we devised a method for handling extremely sparse regions without frequency vectors. In addition, we proposed a method to determine whether we use the frequency vectors or not for each partition. We conducted experiments on 3 real-life datasets and a synthetic dataset. Because a time interval dataset can be represented by a 2D frequency matrix, we compared our algorithm with existing algorithms for publishing 2D histograms. We conducted the experiments with varying the privacy budget epsilon from 0.01 to 1 and plotted the relative errors. In all datasets, tidy outperforms all compared algorithms. In addition, tidy is the second fastest algorithm next to the naive algorithm, which is very efficient. We conducted an ablation study. This graph showed that our refinement algorithm reduces more than 90% of the error. And we can see that the proposed policy selection also contribute to reduce the error. Because our refinement algorithm has lower time complexity than the existing method, our algorithm was at least 23 times faster than the existing algorithm. We proposed tidy algorithm to publish a time interval dataset with differential privacy. To reduce the structural error, we devised the triangular partitioning and the frequency vector representations. We proposed an efficient refinement algorithm to reduce the noise error of the frequency vectors. The experimental results confirm the effectiveness of our tidy algorithm. Please leave your comments or email me with any question. Thank you for watching.